Hemoglobin has the important job of both binding oxygen and releasing oxygen. In order to do this, its affinity, or how tightly it binds to the oxygen, must be tightly regulated. A key thing to keep in mind when you're trying to figure out like what way the regulation should go is that if you want to release oxygen, you need to lower the binding affinity for oxygen. So it can seem a little like counterintuitive, like you need oxygen, so you want to make it bind less. But yes, you want the hemoglobin to bind less so that it's actually releasing more. If you're saying that you have a lower affinity for oxygen, basically you're saying you're better at releasing the oxygen. And if you had a better affinity for oxygen, you'd be worse at releasing it. So if you want to release oxygen to your tissues, you're going to need to have a lower affinity for the oxygen. If you think about binding thermodynamics, you get that curve where at a point you're going to be saturated. And once you're saturated, you can add as much as you want of the binding partner and nothing's going to change. The same applies for hemoglobin. If we look at our hemoglobin binding curves, we see the same thing. We get the saturation. If we look at the oxygen levels in our lungs, we can have a little bit of difference in our binding affinity, and we'll still be practically saturated. That's not going to be the point where we have a difference. The point where we have a difference is going to be more at concentrations that we're actually going to find in our tissues. And so not only do little differences in the concentration have a big difference, but little differences in the affinity have a big difference in the amount of the oxygen that is held versus the amount of oxygen that is released. Remember that although we can kind of think from going left to right of binding the oxygen, in order to have this much oxygen in our tissues, we must, and this much in our lungs, not only do we have to pick up this much in our lungs, but we have to release this much in our tissues. So by having allosteric modulators that are going to lower the affinity, such as our 2,3 BPG, well, here what we're going to do is we're going to allow for more of that oxygen to be offloaded into your tissues. And so having a lower oxygen affinity is actually helpful for if you want to get oxygen to your tissues. So I know it sounds a little counterintuitive and you have to think over it a little bit, but all this comes back to the fact that what we're dealing with is really just these binding sorts of things. In the case of hemoglobin, because we have this kind of like weird situation, not only do we have the allostery, but now we're talking in terms of oxygen instead of just like normal concentrations. And we talk about gases, we're talking about partial pressures. So you might see this written as like the P05, the P 0.5 or something. What that's saying is that's the partial pressure of oxygen at which you have half of your hemoglobin bounds. Remember that because of the allosteric nature, it's not like you're going to have it all be in like this form where you have two bound. Instead, you're most likely to find it in the two extremes. So like the unbound and the fully bound, and kind of have equal amounts of each of those. Because remember, if one binds, the rest are sure to bind. Or not sure, but they're pretty damn likely, because remember, you're going to be stabilizing that high affinity state. Hemoglobin has those two main states, the T state, the taut state, and the R state, the relaxed state. So remember, the relaxed state is going to be the state that binds to oxygen. Think R, think of red, think of the oxygen being red. So that R state is going to be that's bound to oxygen. You can also think about like you're more relaxed if you have oxygen, right? So this is going to be the relaxed form. It's somewhat confusing looking because what's going to happen is you kind of have it more condensed looking in the relaxed form than in the taut form. But the taut form is called taut because it's going to involve more of these salt bridges between the different subunits. But it will have a bigger hole in the central cavity. But the taut stage, this is basically your weaker binding affinity, and then the relaxed stage where you have a higher binding affinity. And what happens is that when you bind that first oxygen, you stabilize the R state, making the higher affinity for the subsequent sites to bind. As a result, in your lungs, where there's lots of oxygen, you're going to be in that R form. And then in your toes, you're going to be in that T form. So remember that if you have no oxygen, then you have a little oxygen bind. what's going to happen is that that's going to increase the binding affinity for further oxygen. So you're going to quickly saturate. Then when you're in your lungs, you're going to stay at that very high percentage. But then when you go the reverse direction, because remember this binding is reversible, well, now if you decrease the oxygen concentration to say the concentration that you would find in your tissues, well, now you're going to have a lower affinity. So you're going to end up offloading a lot of oxygen into the tissues that need it. And having this cooperativity allows you to do that. Whereas if you were only in the T state all the time, you wouldn't be able to pick up enough in your lungs. And if you were only in the R state all the time, then you wouldn't be able to give off enough in your tissues. But by having this positive cooperativity, we're able to do this. Binding to oxygen itself is actually going to help promote the being in that form because of the structural changes it's going to cause. The oxygen is going to bind. It's going to cause that heme to change a little shape. That's going to cause the protein that's holding on to that heme to change shape. And this is going to stabilize the form that is going to make it harder to actually release that oxygen, not just by that subunit of the hemoglobin, but by all of the subunits of the hemoglobin. So basically, you bind to the oxygen, you cause that pulling, you change the shape of hemoglobin. This makes it so that the other oxygen binding sites have a higher affinity for further binding of oxygen. But if you release that oxygen, well, now what's going to happen is you're kind of going to get shifted to that top form. In that top form, you're going to have these salt bridges form, and then this is going to stabilize this form that has a lower affinity for oxygen. So you only need that single binding event to kind of help shift the balance and stabilize it in one form or the other. So if you bind one oxygen, you quickly transfer into the state that you can bind more oxygen. But if you release one oxygen, you get to the T state where you're going to release more oxygen. Exactly what we need. And when we're in this mid-range, small changes in PO2 can make a big difference. So even if someone has low oxygen, we can give them oxygen and quickly help restore their hemoglobin carrying capacity, their oxygen in their blood. If you want to offload the oxygen, however, you want to be in the low affinity state, and so you would want something that would be stabilizing the low affinity state, such as 2,3-BPG, to help you offload that. The affinity is also going to be regulated by the pH through the Bohr effect, where basically at a lower pH, what's going to happen is you're going to have more of the salt bridges, so the ionic bonds between the different subunits of the hemoglobin, those are going to be stabilized. You're going to have more of the histidines be protonated that can then form the links. You're also going to have interactions that come from the carbon dioxide binding itself and all this stuff. But by the Bohr effect, the pH differences, by the 2,3-BPG, these are things that are actually going to lower the affinity for oxygen, which is good if you want to let off oxygen. Conversely, what can happen is that carbon monoxide, well, what that does is it binds, and not only does it bind where oxygen binds, so if it's there, oxygen can't bind, but what it's going to do is similarly to how oxygen, if you bound it, you were able to get all the other ones to kind of bind more tightly. What happens is that if you bind to carbon monoxide, well, now you're going to stabilize the oxygen tight form. And before, we had it so that although the oxygen was tightly held in your lungs, once you got down to the tissues, the oxygen concentration was low enough that those differences, that the oxygen will be offloaded. But what's going to happen is the carbon monoxide is going to make it bind even tighter. And so what's going to happen is it's not going to release. And so carbon monoxide is kind of like the opposite of 2,3-BPG in the sense that it's kind of increasing the affinity for the oxygen, but that increase in the affinity of the oxygen is not a good thing because that means that you're not letting it go. And if you want to let go, well, then you're going to want to have something like 2,3-BPG. The one time we kind of talk about wanting a higher affinity for oxygen is in the cases where it don't have this kind of high excess of oxygen. And where you see that is going to be in the fetus. And so fetal hemoglobin is going to have a higher affinity for the oxygen, so it can kind of pick up and hold on to all of that oxygen in the little amounts that are left after kind of the mom's used her stuff up. But because then there are even lower amounts in the tissues and things, you're still able to offload enough of the oxygen. Interestingly, the difference between the fetal hemoglobin and the adult hemoglobin isn't so much in its natural affinity for oxygen in the absence of modulation, but instead the fetal hemoglobin doesn't bind to 2b3BG as well. And so it's not really affected by that. And so you're going to see that it's going to stay more in that high affinity state. But when we're talking about adults, we're talking about offloading oxygen. We want to be in that low affinity state if we want to offload that oxygen. And yes, we wouldn't want to be in that low affinity state if we were actually in our lungs. However, in our lungs, we have so much oxygen that it's going to be kind of overriding that effect of the 2,3-BPG and stuff. And so you're going to have high amounts of the oxygen be bound. Remember that you're kind of at saturation. No matter how much more you add, you're still not going to change much. And you can go down and down and down. And until you reach that point where you're starting to approach closer to that kind of KD or that P 0.5, well, then you're going to start offloading oxygen. But before that, you would kind of be stuck holding onto the oxygen, which is good if you want to pick up oxygen. But then if you want to release oxygen, you want to increase the off rate. You want to decrease your affinity if you want to offload the oxygen. Remember, to go from here to here, you either have to bind this much oxygen to go this way, but you also have to release that much oxygen in order to go this way. So remember, lower oxygen affinity is good for letting go. Two ways we can actually lower that affinity are with our allosteric modulator, the 2,3-BPG, as well as with the Bohr effect, where if we have a high amount of protons, which means we have a low pH, we are going to be decreasing the affinity, and therefore we are going to be increasing the release of the oxygen. So those are two main ways that we talk about with hemoglobin being modulated in its affinity. And then we have the fact that the oxygen itself is also going to be helping regulate things because of its allosteric nature. In that case, though, we have a homotropic modulator because the oxygen is affecting the binding of further oxygen rather than heterotropic, such as in the case of our 2,3-BPG, affecting the binding of oxygen.